Okay. So I will start. Actually, I have a few slides of introduction, and I'm sure more people will join afterwards. So thanks everybody for joining this webinar, session 2, about Arista knowledge. This is a webinar series we'd like to start to share the, let's say, some experience, some knowledge about surge Arista selection. This is a topic that have been, let's say, requested several times, and I think this is also quite important. So okay, okay. So here's the agenda for today. We will split the presentation in 2 parts. The main part will be, let's say, a brief introduction. I'm going to talk a bit also about the application, and then we will go into the basic configuration of the voltage ratings. So the first part, which will be handled by myself, will be the, let's say, more the electrical part, and the second part, which will be handled by Philippe Raschke, will be more on the, let's say, on the mechanical side. But as you know, it's difficult to split in 2 parts because there are some, let's say, crossing area, like for example, short circuits, which is something in between electrical and mechanical. And we will have a few minutes also. We will try to respect the timing, the schedule, to have times at the end for the questions and answers. So just very brief introduction, and that we have now 110 participants. Just a few slides to wait for a few more people, and then we will, let's say, jump into the technical topic. So important. Maybe there are people in the audience which do not know Tridelta, which are not, let's say, familiar with our company. I'll just make a brief introduction. So we are Tridelta Meidensha. We are proud to share a patient with surge arresters together with Meiden. Meiden is our Japanese mother company with the headquarters in Japan. They have invented the MOV block technology in the 70s, and at the end of the 80s, developed the first, one of the first surge arrestor polymer design. And Meiden acquired the Tridelta Überspannungsableiter in Germany in 2015. Since this time, we are called Tridelta Meidensha. And our factory in Helmsdorf, Germany, has a long history in say, porcelain insulators first from the 19th century, and in the 60s also with the manufacturing of surge arresters, and since 1989 our factory here in Helmsdorf is manufacturing the first metal oxide surge arresters. Our main business is high voltage application for transmission networks. If you're familiar with the portfolio, you're also familiar with those SB series for porcelain design, SBKC series for cage design, SBKT series for hollow core design. And I will show some examples afterwards when we talk about the, let's say, the importance. Actually, the design itself has it's a significant importance when you start, let's say, configuring or selecting a surge arrestor. Okay. Then let's say the second part of the portfolio, which is, let's say, a growing part, because we have a lot of, let's say, innovation and smart guys like Philip doing some, let's say, game changer in the world of surge arresters. One of the main innovation is the SBKW series, which is going to be released officially in the next months. This is a new manufacturing process, and we will probably make a separate webinar presentation about this topic. It provides a lot of technical advantage, but also cost and manufacturing lead times. And this is going to be developed for the distribution class and also to the high voltage application. More details to come soon. Then we have the monitoring with the smart count. There was our first webinar in August 2020 was based on this topic. The smart count, which is let's say advanced monitoring solution for the surge arresters. And then we have special application, which is also an important part of Tridelta business. Also we have a new portfolio to be released very soon for the railway application, and also for the let's say special design that are used as arrestor components for OEMs, typically for cable manufacturers, or let's say OEMs, what we call OEMs, for original equipment manufacturers. Okay, so now we can, so we have about 120 participants. So we will jump into the, let's say, more technical topic about surge arrestor selection. And I would like to give, let's say some brief reminders about the application, because this is quite important. Today we are going to talk about gapless types mainly. We're not going to talk about HVDC, or we're not going to talk about externally gap line arresters, for example. So this is special focus on gapless types for the configuration, which is actually the main application of the surge arresters. So I think most of the people in the audience are familiar with the protection of power transformers, because the transformer is the main asset. We use surge arresters to protect mainly the primary windings. They are, I would say, 99.9% protected with surge arresters worldwide. This is, of course, a very expensive and critical component that you don't want to be damaged due to over voltage. And also, quite often, the transformer windings have the lowest surge withstand voltage. And also, both the primary and the secondary transformer bushings are protected with the same surge arresters in general. And sometimes if you have a neutral point bushings, it's also common to use surge arresters. Another application, which is, let's say, not always mandatory like the transformers, but let's say quite common, is the cable termination, where you often see surge arresters. So this is the transition point between the overhead ground wires and the underground cable. Sorry, the overhead conductors and the underground cables. So for such application, say the protection is dedicated for the cable itself, because, as you know, underground cable are not self-restoring. They don't have a self-restoring insulation. So you want to prevent any damage that could occur on the cable that could bring significant costs for any replacement. And if you're interested for this, you can always contact us. You can also visit the website of Vistera, because we have a common design that's kind of integrated solution together with arresters and cable termination together as an integrating solution. Also for the gapless types, there is also a common application, which is, let's say, largely used, but of course, if you compare to the, let's say, to the number of kilometers of transmission line worldwide, this is only, let's say, a small application. So non-gap line arresters are mainly used to improve the lighting performance on the transmission line to reduce the lightning induced outages. Although the transmission lines are most of the time shielded with overhead ground wires, and they are also, it's mandatory during the erection to achieve a specific grounding resistance to guarantee the lighting performance. Even though you have this, let's say, prerequisites, back flashovers or shielding failures are still an issue. If you're familiar with this topic, it could be quite critical depending on the area, depending on the line, on the voltage level, depending of the chironic level. The chironic level is the density of let's say lightning stroke in a specific area. So basically, the BIL could be exceeded due to lightning over voltage, and this let's say this flashover might cause a breaker operation to clear the fault. So this is important to make also a distinction between these three applications. If I summarize quickly, we have here a very common application to protect valuable assets in your substation. It's kind of mandatory because the transformer is extremely expensive. Then we have a cable termination to protect the cable itself, because this is a kind of sensitive transition point where you don't want the cable insulation to be damaged, which is also associated to significant cost. And then for the line arresters, you don't want to protect the insulators. Actually, you want to prevent a breaker operation. You want to prevent a lightning-induced outage. So this is, let's say one gapless type for three different purposes, let's say. Okay, so there is also we've got very often a question: what is the best for my substation? Should I use porcelain? Should I use polymer? There are different type of polymer. Can you what is the best for our system? Actually, it's quite difficult to answer this question. It's a case by case, but you can see first that it depends also when if you want surge arresters 20 years ago, it's not the same as today. There have been significant improvement over the last 30 years. As you can see in the 90s, one surge arrester for 400 kV system has a weight of 650 kilos. Today, with the improvement and let's say the new manufacturing process that was developed with polymer technologies, we can achieve 100 kilos. And of course, there are also important, let's say, technical features related to the design. So I will go quickly through the different design. I think it's important to, before going into a typical, let's say, a typical arrestor configuration, looking at the voltage ratings, the energy ratings, the mechanical strength, and the short circuit performance and all those things. It's important to understand the different design which are available from the different manufacturers. One of the that you can also find from different manufacturers is called a cage design. It's a polymer surge arrestor where the silicone is directly molded onto the active part. So one of the main advantage, and we also have to be clear, because we are completely responsible for the complete manufacturing process. We are not dependent from the housing manufacturers. So we manufacture everything in-house, and in that case, the silicone is directly molded on the active parts, so it's optimized in terms of weight, and there are, let's say, all the associated benefits like hydrophobicity or pollution performance, which are related to the polymer material. And yeah, so this is say a typical design where if you are looking for application up to 420 kV, if the cost or for you an important factor, a driven factor, and that you don't have specific mechanical strength, because there is a limitation with mechanical strength. This is a fact. This is the reason why we use it mainly up to 420 kV system. And this is basically possible if you have a line drop from the conductor. If you want to use it as a, let's say, as a bus bar support, this is not really recommended. So there is a limitation in terms of let's say mechanical strength. So to summarize, if the cost or a key factor, if you don't have mechanical strength, if polymer is acceptable for you, because you know that it's not always the case. There are still companies, utilities, power utilities using porcelain. So if you accept polymer, then we would definitely recommend to go into this cage design. Then we have, let's say, two design, the hollow core designs. One is the, let's say, very conventional porcelain, which has been used for decades, at least I would say for the metal oxide varistors, I would say 35 years, 40 years. So in that case, you see that there is, this is why it's called hollow core design. So you have a gas volume. Well, actually, this is air at atmospheric pressure inside. So the MOV stacking is in the production process is placed into this tube, and we're using a sealing system to prevent moisture ingress. So these are proven design which are existing before the cage design that I presented before. They have higher mechanical strength. So depending on your requirements, so typically here, if you have mechanical requirements, if you have some seismic requirements, if there are some seismic activities in your countries, or if you have very specific short circuit capability, we would recommend to use the tube design, SBKT tube design on the right side. Of course, this is a polymer design in some countries where the polymer is not largely accepted, still not largely accepted. In that case, it would be the solution would be to use a porcelain solution. And maybe Philip can give during the short circuit part. Maybe Philip will probably explain the difference when you do a short circuit on a porcelain in comparison to a hollow core polymer. One important point also that Tridelta is using, Tridelta is working with many suppliers from Europe. So we have the possibility to provide this preferential origin for special, let's say, custom tariff if required, because it's quite it's not difficult for us to guarantee this preferential origin with 70% of the components which are coming from Europe. So now we'll talk about the zinc oxide varistors or metal oxide varistors. So everybody knows that this is the core component of the varistors. They have a very special characteristic, a unique characteristic, which is a non-linear function. I will go into the details, but basically they behave as an insulator under nominal voltage, and they are able to conduct extremely fast. The transient of a voltage is so in a safe way. So yeah, in that case they divert the energy to the ground in microseconds, And this metal oxide technology or zinc oxide technology is really, let's say, a proven technology which exists, as I explained at the beginning in the introduction, was developed by Meiden in the 70s, and let's say is a very common application since the 80s. So we can say that at least it's a technology that has demonstrated its performance for at least 40 years. And also, I like to state that arrestor manufacturers are basically artists of MOV staking, ZNO staking, because at the end, this is the main challenge. This is the core competence of arrestor manufacturers. We play with those blocks. We play with the diameters of the block in relation to the energy ratings. We play with the height, with the number of block, to define the voltage ratings. And of course, there are some important tests related to this because they have to handle search duties. So they have to dissipate the energy. And so you might see different heat dissipation depending on the design. Okay, so as I said, this presentation is specifically dedicated for AC arresters, gapless AC arresters. The most, let's say, most of the information, if you want to know more about surge arresters in general, the best recommendation I can give you is to read the standards. There are a lot of valuable information. The IC 699-4 is the standard for design and testing of surge arresters. The -5 is for the selection and the application. There are a lot of important information. So most of the time when you see presentation for manufacturers, you just take the information from the -5 actually. And then also I stated this IEEE standards, because since July 2020, there is almost full harmonization with IC. And this is, let's say a good step for most of the manufacturers and the user, because this makes a sense, right? The physics is the same in North America or in Europe, in Asia, everywhere. So yeah, so I highly recommend you to go into the -5 if you want to, let's say, to go deeper in those topics. Arrestor selection is deeply related to installation coordination. In green, you see the withstand voltage of the equipment, for example, the power transformer, let's say the withstand voltage of your windings, for example. Here on the x-axis, you see the switching of a voltage in this area and the lightning of a voltage in this area. So as you can see, that the lightning impulses, switching impulses, are critical transient of a voltage that can break down the electrical strength of your equipment. So this is this part here. We don't want to exceed this electrical strength, the withstand voltage of the equipment. Therefore, we need to use surge arresters. So by using surge arresters, you see now the expected of a voltage are limited on the blue curve here. And I give you a good example. So it's a good application. Afterwards, I will show you a bad application. So typically a BIL is the installation level, lightning impulse installation level of the equipment. For 520 kV system, a typical value is 1,425 kV. If we take a surge arresters with 360 kV rated, the protection level, the residual voltage of the arrestor at 20 kA at nominal current is 933 kV. With such a configuration, you have a safety margin which is higher than 40%, which is a recommendation by IEC. So then you're safe. This is what you want to achieve. So this is the key. I think once you understand this, once you understand that you need this, you always need to be below the BL. Say that you always need your residual voltage to be below the BL of the system. Then you understood everything. We don't have to go further. But basically, this is the key. Yeah? It could be obvious for many people, but it's still misunderstood because this residual voltage could be used also to go further. And this is what we discussed in the last webinar about insulation withstand. So we'll not develop too much unless you have questions at the end. Here I just want to, let's say, to display, to show the typical ratings for gapless types according IEC 699-4. So the rated voltage, the continuous operating voltage, UC, and these are actually, if you want to specify surge arresters, and these are the, let's say, the important ratings. We also have the temporary overvoltage for 1 TOV for 1 or 10 seconds. We have a nominal discharge current. So also it's important that when you see nominal discharge current, sometimes 10K, sometimes 20K, it's not related to the performance of the arrestor. It's used for the classification. It's only used for classification. We need a kind of reference for the light. This is actually a typical lightning current. We want to use a reference to classify arrestors. Then you have, as I said, the most important characteristic or rating of the surge arrestor, or the residual voltage, or the protection level, which is also related to a specific lightning impulse or switching impulse value with a specific wave shape defined by the standards. Then you have two important energy ratings that I will develop afterwards, the repetitive charge transfer and the thermal energy, WTH, coming from the operating duty test. So I will give you, I'd say, a typical configuration. It's always difficult to go into the details. Otherwise, we need 2 hours only to talk about, let's say, voltage ratings. And I think this is not the purpose today. I'd like to give you an example for a 420 kV system with a solidly grounded neutral point. So this is important. This neutral grounding system is also a key point for the voltage rating selection of the arrestor. The reason is that let's say, for a typical solidly grounded system, you have a, let's say, a low TOV value, and when your system is let's say is grounded, is going through an impedance or is insulated, you normally accept higher TOV value, and this is actually the main reason. So we use for a grounded neutral point, we use a typical Earth fault factor of 1.4. So maximum face-to-face maximum face-to-face voltage is 420 kV, and as if you're not let's say, if you're not a specialist, it's the ratio between a face to ground and face to face is square root of 3. So the maximum expected voltage face to ground for a 420 kV system is 242. And as you know, for such application, the surge arrestors are always connected from face to ground. So then comes the calculation for the UC, often called MCOV, for maximum continuous operating voltage, which is actually, this is a term coming from the IEEE standards, but in IC it's UC. So we use a 5% safety margin coming from disturbances and harmonics to define the minimum MCOV or UC that you need to use for the surge arresters. In that case, is 255 kV. Then comes the selection, or the definition of the rated voltage, UR. So we need to consider, in that case, the MCOV. So there are, as you can see, there are two possibilities, let's say. And that's why you have the, let's say, UR1 and UR2. The first method, let's say, is quite simple. It's a factor of 25%, which is, let's say, well-known accepted factor, which is coming from the MOV manufacturing, or let's say MOV properties, would be better to say it like this. MOV properties, because I will develop a bit further, but a rated voltage is actually a temporary over voltage. So basically this ratio is the difference between, I say the ratio between the capability to withstand an over voltage for 10 seconds with the capability to withstand a continuous voltage, a power frequency continuous voltage over its service life, so for 30 years, let's say. And this this performance, let's say, is more or less the same for most of the zinc oxide varistors. So therefore, it's quite, if you want to make a quick calculation, it's quite common to use 125. So UC times 125 gives you the minimum rated voltage. But there is another way also to calculate, and I think this is important to understand what the rated voltage means, is to consider the TOV value for 10 seconds. And this is what the calculation shows here. By using this, let's say this TOV, let's say this example of power frequency versus time characteristic, you can define, let's say, this the required rated voltage in a different way. And this is quite important because there is often a confusion between a rated voltage, which is, let's say, often associated to the nominal system voltage of an equipment, let's say. But for surge arrestor, it's different. A rated voltage is a TOV capability for 10 seconds with prior duty. And I will, let's say, give an example afterwards for the transition to Philip for the operating duty test. Okay, so now you have, once you have defined the minimum UC, MCOV, and minimum rated voltage, it's quite common also to select standard ratings from arrestor manufacturers, and this is also, let's say, also quite standard to use, let's say, standard rated voltage that can be divided by 3. So you can see here from our porcelain SB0 type catalog, I have selected some examples for 420 kV. So here we have 336 kV, it's a possibility. And here we have 360 kV. And here I also selected this one because I would like to show you what is happening if you are taking a surge arrestor with a very high rated voltage. So you can see here for each selection the different protection level which are associated, because this is the next step. Once you have defined your rated voltage, you have to look at the associated protection level or residual voltage to make sure it fits to your system. And before giving you, let's say, an example of bad configuration to make sure the example is clear, I want to show you this curve. I'm sure that most of you are familiar with with this voltage current characteristic. So on the x-axis you have the current through the surge arrestor, and on the y-axis you have the voltage peak value across the surge arrestor. So it's important to define two areas in this diagram. The first area at the bottom left should be called the operating area. And the area here on the top right should be called the, I don't know, protective area, because most of the time, you know, the surge arrestor, you are in the point is in this area, right? Is the UC. This is the maximum continuous operating voltage. So basically, in real life, you know, this point is always here. Yeah, and the surge arrestor can withstand this voltage let's say across along its service life. Sometimes, if you have a TOV value, you are going in this area, so you can go up for a TOV value for a few seconds, then it goes back to the operating point. And this is fine. But the surge arresters is actually used to limit over voltages. So quite from time to time, you have a switching or you have a lightning impulse, and you go very quickly, few microseconds in this area. And you want to make sure that you know, you don't exceed the BL of your system. And this curve is important because there is a ratio between, for each MOV block, there is a ratio between the protection level and the rated voltage of the arrestor. And basically this ratio, to make it simple, is the ratio between the, let's say, the over voltage protection and, let's say, the operation behavior. The best way would be, of course, and this ratio is in the range of 2.2, 2.4, let's say, depending on the block size and the, let's say, the block characteristic. But this is one of the, let's say, the key when you manufacture blocks, because everybody would like to have a high TOV value, that the surge arrestor can withstand high TOV with a very low protection level. But of course, this is not possible. And that's why I want to give you this example. So let's say for your 400 kV system, you would like to have a very high TOV value. And from this TOV value, you select a rated voltage from the catalog, which is 396 kV rated voltage. This rated voltage will give you a protection level at 20K of 1026 kV. But here's the problem. If you use such a surge arrestor on your system, you will have a safety margin which is below 40% in comparison to the BL of the system. But okay, I mean, this is a bad application, a bad example, but most of the time, nobody is using 396 kV. But it's quite common to see in specification very high TOV values, which are not related to the rated voltage. So it's important when you specify a TOV that you also consider the rated voltage. And as a manufacturer, we can provide typical curves that give you some guidance in this direction. About the time, Philip, we are good? Okay. Okay, so now comes the energy ratings. So just to make the transition a little bit better. So we have here, as I said, from time to time, and this is the reason why you use surge arresters, from time to time, you will expect lightning impulses and switching impulses on your system. And you have defined a rated voltage. you have defined the residual voltage that gives you the confidence that your system, your power transformer, your cable termination, your line is protected, okay? But you have to make sure that the energy which is coming from lighting or switching will not exceed the MOV properties. And this is why now comes two important energy ratings. One is called repetitive charge transfer with a QRS rating. This is a new introduction from the IEC 699-4 from 2014. This is, let's say, a rating which is mainly associated to lightning surges. And basically, the idea here is to have a kind of statistical approach to look at the, let's say, the mechanical integrity of the blocks after lightning surge injection. So we take 10 blocks. This is what the standards, the AC standards defines. We take 10 blocks, and for each block, we have to inject 20 impulses. And this here, this let's say diagram shows a typical, let's say the typical process that you do on each block. So before each test, you do a kind of, let's say, initial measurement or initial characterization of the block with residual voltage and reference voltage, which is actually these two ratings which are done in the written test of the arrestor. And then you will do the injection of the lightning impulses, or let's say a typical lightning impulses. And then once you have, let's say, once you have applied the stress, the required stress, you will do a final characterization, which is actually a pass criteria, where you want to make sure that you don't exceed the initial measurement. Okay. So this is what I said, just to summarize. So this is, you want to make sure that the MOV block keeps its mechanical integrity, because you don't want to see a block. There is also a visual identification. You don't want the block to be broken, to be damaged. And sometimes you can see it. If the energy is too high, you can see visually the damages. Yes, and this is the difference with the next the next energy test, which is called thermal energy from the operating duty test, which is more, let's say, a test to verify the thermal recovery. So, and this is more related to a switching, to a breaker reclosing operation. And actually in the IC, sorry, in the IEEE standard, it's called switching impulse energy rating test. Yeah, so, but in the IC, it's called thermal energy test. So as I said, mainly associated to switching. So there is a formula also in the, you see in the -5, what I mentioned. If you want more details, there is an annex in the -5 that can give you all important information to make such calculation, what is needed on your system. Okay, today I think most of the power utilities, all the consultants, they are using PSCAD, EMTP software to run such simulation. So you don't need to do it manually, but this is quite, there was, let's say, also a change in the new IC standards also because, let's say, on the one hand, those requirements are coming from the power utilities, or from the, sometimes power utilities are working with consultants doing such simulation. As a manufacturer, we cannot tell you which energy you need for your system, or let's say, which energy needs to be absorbed by the surge arresters considering your system parameters. we can only tell you, well, we have done the test on our block and we can give you the confidence that this block will withstand this energy. And one of the change in the IC was to also to harmonize the, let's say, the simulated value or the calculated value together with the test which is done by the manufacturers. So yeah, here's let's say a typical example for 420 kV system where you need 7 kilojoule per kV rated. So it's important to see that this is kV rated. And the reason is, I will, let's say, show here. This will be the last part of my presentation, of my section. So you also have a kind of typical, let's say, test process here with initial measurement, preconditioning, preheating of the blocks, because you always want to be in the worst case scenario. So here is the injection of the energy. So if you need 7 kilojoule per kV rated, we will, this is the here the part where we inject the energy. And after the energy injection, the arrestor needs to recover. After injection, the temperature is quite high, and then you have to apply the rated voltage for 10 seconds, and then you have to apply the maximum continuous operating voltage for 30 minutes. And you want to make sure that the temperature is going going down. That's why we say this test is to verify the thermal recovery. And then afterwards, of course, it's a very typical process. You repeat, in that case, the residual voltage test to make sure that there is no change in the protection in the protection properties. Okay, so yeah, and just to make the transition, here, what you see here, when we talk about TOV value with prior duty is actually this preconditioning and pre-stress coming from the operating duty test. So it's different when you do a TOV on a, let's say, on a surge arrestor without preconditioning and with preconditioning. And yeah. So yeah, that's all for my part. I will now hand over to Mr. Philip Rashke. And okay.
Okay, everyone, welcome back. It's my part now. Thanks for the transition, Florent. TOV, especially when we talk about energies that the surge arrestor has to be capable of, TOV can be a critical part when it's higher than expected. And in cases where the surge arrestor is selected for a grid that perhaps has a higher TOV than expected, or where lightning or impulse or switching impulses provide higher current densities or higher charge than expected, it can happen that the surge arrestor is not capable to hold this voltage or current. So in that case, the surge arrestor can break down. And that's the case when we talk about a so-called short circuit. So the surge arrestor will go into a short circuit mode. The resistance of the surge arrestor goes down. So all the energy of the line, of the connected line, can flow through the surge arrestor. not only the specific line parameters can cause a short circuit on the surge arrestor, also an aging surge arrestor. So if the zinc oxide blocks are affected by an aging process, or if there is a problem with humidity ingress into the surge arrestor, if we have a hollow core surge arrestor, then we can also see arrestor failure due to thermal runaway. So heating of the continuous heating of the zinc oxide column, and then it gets thermally unstable, and the pressure is rising, and the housing is ejecting the hot air, and the current is flowing across the surge arrestor. A high current is flowing across the surge arrestor or across air. And this can also happen due to humidity ingress when an inner flashover occurs. So there are several reasons for having a short circuit on the surge arrestor. And that's why our product standard 699-4 defines a short circuit test, where we have to provide a result of high current, like the short circuit current, where the surge arrestor goes in a kind of destruction mode, but does not destruct violently and then endangers its surroundings. And this is an interesting thing. I want to talk a little bit more about this. We can select the surge arrestor, or you can select the surge arrestor according to its short circuit capability. Important criteria are amplitude and time of the short circuit. So mainly this has something got to do with the time until the fault is cleared in the grid. So we are seeing an amplitude depending on the capability of the grid, and we are seeing a time depending on the time when the fault is cleared in the grid. And this leads to always to a combination of current amplitude and time for this short circuit current. And the standard defines a rated short circuit current, which will be always the selection value. And there is a reduced and a low short circuit value, which belongs to a specific rated short circuit. You can see it here in this table. For example, a very typical value for 20 or 10 kA discharge class or station class surge arrestors is 63 kA rated short circuit current. Sometimes it appears that that you see 65 kA, which has been an older specification. So if 65 kA is on the test report, 63 kA is also covered. Of course, it's a little bit higher. And then we also have to test 25 and 12 kA. And we also have to test 600 amps with a total duration of 1 second. So that's very long for a current like this. It's also challenging to withstand currents like this. It's more than a TOV condition. It's already so much current that the surge arrestor will most probably flash over if it's stable enough, and tends to burn for a couple of seconds, so it's much energy. And you see here on the right side, very nice picture we have recorded in a test lab under short circuit conditions. So the current has already left the housing of the surge arrestor and flows across the air. So the air is ionized, and all the short circuit current the line is capable of flows along the side of the surge arrestor. And as Florent told you, we have different designs. For example, the tube design and the porcelain design for surge arrestors with gas volume. And we also have surge arrestors without gas volume, like the SBKC or SBKW type. You see here in the two pictures on the right side. And for those different surge arrestor designs, we have to provide a kind of pressure relief function, because in each case there is an inner pressure occurring, because if you have that kind of energy, 63 kiloamps, 63,000 amps, material will melt, and this molten material will turn into a gas, very hot gas, and also for the surge arresters with gas volume, naturally this enclosed air will try to expand and will put pressure on the housing. And this can be very, very dangerous, especially for porcelain house surge arresters. So in the past decades, people learned the hard way that that especially porcelain house surge arresters can explode like a bomb, and all those fractured parts will fly around and destruct everything which is in the surrounding. So we have to make sure that this doesn't happen. That's why we include a kind of pressure relief device to hollow core surge arresters. On the left side, SBKT. It's a very nice example, 80 kA short circuit test. You see this this wide opening, and you also see that internally there's something defective, and this is a membrane that provides tightness to the surge arrestor, but under short circuit condition, it will open and it will release all the pressure, all the hot air to the outside, and then it has a certain shape, like you see on the right side, the not on the right side, on the middle side, the SB0. We have the pressure relief device with a certain direction to the lower side of the surge arrestor. So the air that is ejected, it will come out and it will have the perfect direction to meet the outcoming gas from the other side of the surge arrestor, and it provides like a canal where the whole short circuit current can flow across the air. So the surge arrestor protects itself by releasing the pressure and by creating a conductive path outside of the surge arrestor. What is impressive on the left picture is that this plate we see, this bent plate we see on the low side of the surge arrestor, is a 20 millimeter thick steel plate. So there is much force provided by this inner pressure, just to explain how much energy, how much pressure is created inside the housing. And we see the two pictures on the right side, SBKC and SBW. There the pressure relief works different. We have a soft shell, which is easy to destroy. You only have to make sure that the inner parts don't fly out, like the MOV blocks or aluminium parts. So those designs provide a very strong, very, very rigid housing, protecting inner parts to come out, but also providing a pressure relief by a kind of membrane behavior. So this is our design capabilities and our more or less our secrets, how we provide a non-violent destruction in short circuit mode, also for big currents. Short circuit currents, and have been rising in the past years because the short circuit capability of the grids are rising, and that's why we have to provide surge arrestor designs that cover all of the requested rated short circuit classes. For 40 kA, the SBK0 is valid, SBKW is tested up to 50 kA. And then we have the SBKC2, which is tested 63. Actually, it's tested 65 kA, so we cover 63. And all those other designs, SB0, SB1, SB2, 63 kA. And then we have the tube design, 63 kA. And we have the amazing SBK-T2, which withstands 80 kA short circuit current. And that's an interesting test, and we want to show you how it looks like. We want you to be a part of the test virtually. One of the most interesting things of of our job, the short circuit current. Let's hope this works. It doesn't, but we have a interlink here. Florent, can we see the video? Yes. So I'm not sure if you can hear the noise, but as you see, this is an explosion for the spectator. 80 kA, 0.2 seconds duration. When you attend to a test like this, it's like a mix of explosion and earthquake. So that's how much energy is inside this current. And now it gets even more interesting, because we are recording this test with a special camera, a high-speed camera. This is not working as well. We have the link here. And this is about 50 frames per second. So you can see the 50 Hertz wave pulsating. You can see how the current is flowing through the air, through the ionized air. And what we also see is that there is a surge arrestor in the middle, and it's from its structure, it's not destroyed. So there is the membrane is opening, the pressure can release, and the surge arrestor is still more or less intact. The housing is not fractured, and this is what we have to confirm during this test. Okay, coming to another topic, which is important for the design and the selection of the surge arrestor. The topic is weather resistance. So I chose this headline because there are many things to consider, especially when it comes to demanding environmental conditions, like regions with high air humidity and rain, what we understand as tropic area. We have extensive UV light exposure, like in the desert. We have salt fog, like in coastal areas, dust and sand. Especially sandstorm is a very critical thing when porcelain house surge arrestors are used, because it's like a sand blasting to the housing of the surge arrestor. We have ice and snow, and we have to consider industrial or even organic pollution, which takes place on the surge arrestor surface. And those impurities on the surface, they can lead to conductivity, and then surface currents flow across the surge arrestor. And we will have more or less a kind of tracking and erosion process to the surface that is damaging our surface and decreasing our potential insulation withstand of the housing itself. And of course, we have a high risk of flashover when the surface is humid and polluted and current is flowing. And perhaps it's possible that this current ignites an arc across the surge arrestor housing. So this is the risk. And we have to cover this. We have to consider this by using this typical shed profile of the surge arrestor. And this shed profile provides us a so-called creepage distance, which is the way we are going from the top connector of the surge arrestor down to the base flange or base terminal. And we have to go all the way across the insulator, across the sheds, and this is understood as creepage distance. And this allows higher insulation and increases the insulation capability of the surge arrestor and decreases surface currents, and therefore decreases the conductivity. And here I have a very nice picture from 1897. This is a post insulator which has been developed and patented 1897 in Hermsdorf. Our company was not existing. We had a porcelain manufacturing here, but we didn't had Tridelta Meidensha yet. But they were inventing a porcelain post insulator that can handle a certain voltage, but that had one special housing. It has this triangular shape. That's why it's called delta bell, and it has sheds. And on the top of the sheds, there's rain, there is ice, there is snow, there is everything. But on the lower side, it's dry. And this area is covered by the sheds, and this area will not have leakage current. So that's the first patent of insulator like this. And one interesting thing, 1897 developed in Hermsdorf. We have sheds number 1, 2, 3, and it's shaped like a delta. So this is where our name comes from, Tridelta. I don't know if you have known, Florent, but I wanted to provide this very, very important information here in the presentation. So we are talking about creepage distance, which gives us pollution performance. And when we want to select a surge arrestor for with a specific pollution performance, we have to standardize this, and this is done in the IEC 60815, which gives the unified specific creepage distance in millimeter per kV. So the bigger the rated voltage of the surge arrestor, the bigger the creepage distance has to be, and this is classified. We have class A to E, and very light pollution area for areas where typically it doesn't play a role, there's only rain. So we have a, normally we use a specific creepage distance of 25 millimeter per kV. And then we have light pollution, medium, heavy, and very heavy. And the specific creepage distance is rising according to this pollution area. Another topic I want to talk about when it comes to weather resistance is hydrophobicity. Earlier we had the question, what is the actual advantage of a silicone house surge arrestor? And it's actually, I don't have to explain, you only have to watch the picture I have put on the slide here on the right side. I want to explain you more in detail where this comes from. So porcelain housed surge arrestors are more and more replaced. We are by silicone house surge arrestors. So we are facing a big trend to HTV silicone in the past 10 years. So the market is moving to silicone strongly. And the reason for that is the excellent pollution behavior, and of course also weight and price. But now we're talking about pollution behavior, because the silicone has a hydrophobic effect. Like you see on the right side, the pollution does not stick on the surface. The water, it remains as discrete droplets, like you see here, and not as one complete humid layer. It's only discrete droplets. And the arrestor cleans itself during rain. You see here this one droplet going down the shed and cleaning the surface. So this is the magic of the properly molded silicone house surge arrestor. To make my arguments even stronger, I show you a test we have performed in the past years, artificial pollution test with very harsh requirements we know from the coastal area and the desert. So much salt fog, high humidity in morning hours, temperature, contamination, and so on and so far. And we put two kinds of surge arrestors inside, one porcelain house, one silicone house surge arrestor, with the almost exact the same creepage distance and the same rated voltage. So the conditions are the same. And on the bottom, you see our smart count device connected. So it will record the leakage current and the surface current of the surge arrestor. And then the test started and salt fog is injected to the chamber here on the right picture. And you will see on this diagram here on the left side, the behavior of the current of the porcelain house surge arrestor. We have this area before this green bar. It's the condition before the test starts. So we have 1 milliamp total current flowing, very stable. And then we switch on salt fog, the salt fog artificial pollution test. And then each time when the time of when the salt fog is switched on, the surface current is rising. So it's not the leakage current through the zinc oxide block, it's the surface current that is spiking up here. And actually those spikes are increasing. So if we have proceeded with this test, we would see a very strong upwards trend of this surface current. And now I show you the same diagram at the same time for the silicon host surge arrestor. There are no spikes. So the surface, it's non-conductive, and this is the very, very clear confirmation of the hydrophobic effect of the silicon host surge arrestor. You only see MOV current, 1 milliamp standard. One other property of the surge arrestor we always have to consider when we select or when we design a surge arrestor is its bending strength. Bending strength is required because those surge arrestors are typically affected by mechanical loads. We have strong leads that are bent down to the surge arrestor, which provide a static force to the surge arrestor. We have surge arrestors which are not equipped with post insulators in the direction of the line. So the line itself has a direct influence to the mechanics of the surge arrestor by its weight and by the vibration of the transmission line due to wind loads and yes, short circuit current. We have wind loads on the surge arrestor itself. We have electromechanic force on the line. And we also have seismic vibration on the ground terminal of the surge arrestor. So those things have to be considered when you design a surge arrestor. And of course, there is standardized, there are values we have to fulfill to classify our surge arrestor for certain applications. For porcelain housed surge arrestors, typically the value MBL plays a role, mean breaking load. So normally 3 samples are tested, and you are applying a force vertically. On the picture here on the right side, you can see like this this cylinder, this hydraulic actuator pushing the surge arrestor on the top. And on a certain point, the porcelain will break, and you record the force or the moment which is applied on the bottom terminal, or which is created on the bottom terminal. And the mean value of those 3 breaking loads will be recorded and then is the same like the MBL value. So MBL value means the mean value of all 3 breaking loads. Then for porcelain housed surge arrestors, but more also for polymer housed surge arrestor, the SSL value plays a big role. SSL is the specific short-term load, which means the maximum force that can be applied for a short time on the surge arrestor without causing a mechanical or electrical failure. And typically the test looks like this. Here we have an SBKW design, and we pull on the top. We pull until the SSL value is reached. And then we hold this value, and then we decrease the value to 0 again, and afterwards the surge arrestor has to be electrically and mechanically intact. Then we have the SLL value, those don't mix them up. Specific long-term load, normally this is lower than the SSL because this value is the maximum force that can be applied continuously, not only for a short time. And this value, this specific value is tested in a 1000 cycle test. So the surge arrestor is bent up and down 1000 times. And it has to be electrically and mechanically good after the test. And then some other things are done, like a thermomechanical preconditioning is a very interesting test where different temperatures and different force directions are tested. You see here an apparatus like this standing in a climate chamber where the temperature goes to 40 degrees plus and to minus 40 degrees, or like we have tested very freshly, minus 60 degrees is also challenging in this test. One thing we have to test as well is the silicone adhesion. This is integral part of the bending test. And of course, silicone adhesion plays a capital role for the insulation strength of the surge arrestor. If there is no adhesion, water can ingress, and water will definitely produce a conductive part and will lead to a breakdown of the surge arrestor very early. So we are doing a boiling test. Surge arrestor is held under boiling salt water for 42 hours. So that's a very, very harsh condition for the surge arrestor. And afterwards we do an electrical measurement. But what we also do is a peel test. So this is what we provide during our normal manufacturing. This is a quality test we internally conduct. It's not standardized, but it's a kind of quality assessment. And another test is the pull-off test, and therefore I had a little competition with my colleague Florent, and he made a bet that he could take a random surge arrestor, silicone host surge arrestor, out of the production, and he could easily pull off the silicone to show me that our bending strength, our silicone adhesion is not good, and I accepted for this bet. So he took a random surge arrestor from our production and he tried to make the pull off test, and here in this wonderful picture you can see on the pain in his face how he struggled to get off the silicone. So what I want to tell you with that is that we are taking special care for the silicone adhesion, and we are testing it regularly, and this is a very basic feature of the Tridelta surge arrestors, that they provide a very good silicone adhesion.
Can I make one comment?
Of course.
As you said, it's a key. As you know, most of the, let's say, the main cause of failure for surge arrestors is moisture ingress, yeah, what you see on the picture is a SBKW type also, which is let's say has a different manufacturing process than the cage design. And since we want to use it also for distribution class, it's a key, let's say for me, it's a key point to make sure that we apply a kind of quality check to prevent moisture ingress, because you can pass a type test, but if you compare this to the composite insulator production, you will see that the standards of composite insulator, it's much more demanding than surge arrestors in terms of bonding performance, adhesion performance. And this is something Tridelta would like to implement because we believe that the IC is a little bit too weak. Just wanted to state this.
Okay, I will speed up a little bit to fulfill our time schedule. Bending strength examples for our designs SBK 0. We provide SLL and SSL value going from 1000 Newton meter SLL and 1200 Newton meter SSL for the SBK C0, up to 10,000 Newton meter SSL, SLL, and 25,000 Newton meter SSL. So we cover a very wide range of mechanical forces with our product range. One mechanical consideration is the seismic performance of the surge arrestor when they are installed in areas where earthquakes can occur. And important design parameters are bending strength of the surge arrestor, as explained, the length and the weight of the surge arrestor, and the damping behavior. And there are actually two ways to confirm the seismic performance of the surge arrestor. One is calculative. We can calculate the mechanical strength under seismic condition. And we can also provide an earthquake test. And on this point, I want to explain a little bit more. Earthquake test consists of 3 steps. We have a static pull test to calibrate the test equipment. So we pull on the surge arrestor. It looks like this. You see how this surge arrestor is bent under the strong force of the pull test. And then we release it and the surge arrestor will snap back. Then that's why it's called snap back test. And when a system is, when an impulse like this is applied to a mechanical system, it will swing in its natural frequency and you will see the damping behavior. So you have this downwards curve, this this oscillation going down. So this is what we have to do as second step. And then, as you might see in the picture, the surge arrestor is placed on a so-called shaking table, a big hydraulic table, which can apply a certain acceleration, ground acceleration to the surge arrestor. And with that table, we are shaking in different directions with different accelerations, and we can go from a very low frequency to a higher frequency. And during this, on the top of the surge arrestor, there is a sensor, and you will see that there are different natural frequency, one fundamental frequency, and more harmonic frequencies, where the surge arrestor is swinging with the highest acceleration. And this highest acceleration we take, and then the surge arrestor is, the ground acceleration with this frequency is applied to the surge arrestor by the shaking table. Typically, this earthquake test is done with a ground acceleration between 0.25 G and 1 G, depending on the requested level. There's design or performance level. And we have to consider some factors, which are, let's say, security factors. At least we take 2. So we multiply the requested bottom acceleration with 2 or more. And a typical case we have here, 0.5 G requested multiplied by safety factor 2 or elevation factor 2. We will test 1 G bottom acceleration. And now I hope this will work. It's not. So maybe we can do it after the webinar. Very sad. We will waive it. So this is the test setup. We have the shaking table on the ground, we have the surge arrestor, and we will apply the bottom acceleration, and the surge arrestor will swing and will have a high amplitude on the top. And at the end of the test, it has to be structural and electrically in a good condition, so it shall not change its properties. Insulation withstand level is also an electrically and mechanical parameter you have to consider when designing and selecting a surge arrestor. But to be honest, we have spoken very much about that in a separate seminar. So I would invite you for this topic, which is a complicated topic, to look on our YouTube page. You just have to type in Tridelta Meidensha, and then you take your mouse and you click on session 1, and there you will have all the information about withstand voltages, altitude correction, and clearance calculation. Okay, I'm coming to an end, and one thing that has been asked for in the last webinar was how long can a ground cable of the surge arrestor be? And I want to grab this question and answer it right now. So here on the right side, we see a typical installation of a porcelain house surge arrestor. You have the insulation base, so the surge arrestor is galvanically separated from the steel support. And then we have the ground conductor, it's insulated and it goes down here to a surge counter. And then the surge counter is grounded by a separate ground conductor. This ground conductor is 1.2 meters long and this one is 0.3 meters long. And the steel structure is the boundary condition, it's completely grounded. So we assume that the complete conductor will be 1.5 meters. And we will make an example for the calculation of how the residual voltage of the surge arrestor rises by the length of this cable. So typically we have a discharge current of 10 kA. The wave shape is 8-20. That means the rising edge is 8 microseconds long. So we assume that 8 microseconds is the change of the current, that the change time of the current. And at this condition, we have 465 kV for this example. I think this is typical SB porcelain surge arrestor with SM classification. And we have a conductor length of 1.5 meter. And as a rule of thumb, we assume that the conductor inductivity is around 1 microhenry per meter. So there's a very standard formula of the electrotechnique, the voltage drop across a conductor with a certain inductivity at a change of a current with a changing time of the current will provide you a certain voltage drop, and this is 1.5 meter times 10 kA divided by 8 microseconds, and I think I forgot the inductivity here on this on the thing. So we have 1 microhenry, and the result is that the voltage drop across this cable, along this cable, will be 1.9 kV in this condition. So two things we have to consider. One thing is the safety aspect. So that's why you should never touch the upper conductor of the surge arrestor. So under lightning or discharge condition, there will be a dangerous voltage drop on the conductor, even that it's grounded. And the residual voltage of the surge arrestor is changing. 465 kV initially, plus 1.9 kV for the inductive voltage drop. We will have the result of 466.9 kV. So you can calculate by your own and then recalculate the protection level that is provided by the surge arrestor and compare this to your BIL of the system, of the transformer, or whatever you're protecting with the surge arrestor. It doesn't play a role where to put surge counter. You can put it on a height where you can easily read it. The conditions stay the same. One last topic we are asked about very often. Do I need a grading ring, or can I use a grading ring? Questions like that are raised. And what's the difference between a corona ring and a grading ring? For some of you, it might be clear, but for some not. So I will explain. I will start with the corona ring. Corona ring is always on top of the surge arrestor. You will never see it hanging down. And the corona ring will improve our so-called RIV performance. RIV is something that comes from the EMC standard. So electromagnetic compatibility. Sorry, it's when your tongue is slower than your brain. So when we apply voltage to an electric device, it will have a kind of electromagnetic behavior, and the higher the voltage, the stronger this influence is. And then the design of the surge arrestor is of interest, because if you have sharp edges, they behave like an antenna, And something happens that we call external partial discharge. It's like electromagnetic waves are coming out of the surge arrestor upper part, and we want to prevent this because this is producing radio interference. And that's why we are applying a corona ring, which is somehow shielding the top of the surge arrestor with a very round shape. So this is the best shape you can have to cover the surge arrestor from for the electric field and to prevent RIV or corona to appear. Okay, and secondly, don't mix it up. We have the grading ring hanging down on the surge arrestor. We have a very classic installation here. This is providing a so-called grading performance. The surge arrestor has a specific length and a voltage on top. And the zinc oxide blocks, they have a capacitance from top to the bottom, but they also have a capacitance from top to the sides. So that's what's called stray capacities in the electrotechnique. And through those capacities, a current is flowing because we are living in the AC world. Current can flow through the air, through capacity of the air, and also through the surge arrestor itself. So we have a resistive, capacitive voltage distribution along the surge arrestor. And the highest capacities, they occur on top, so the highest currents do flow on the top surge arrestors. All the capacitive current and resistive current that flows through the lowermost zinc oxide block has also to flow through this. So all those on this diagram, we have 54 MOV blocks. All those 54 MOV blocks have a capacitive current and a resistive current, and the top MOV block has to take all the current of those. So the voltage stress to the topmost varistor block is the highest, and on the lowest varistor block, the stress is the lowest, and that's why we have this diagram where we see that the distribution goes very high from the top MOV block to low on the low MOV block, and we can have an influence to this voltage distribution by applying a grading ring on top. You see on the diagram here on the right side, we make a FEM analysis where we see the voltage stress and how we can shield the voltage stress, how we can improve the distribution along the complete surge arrestor length. The best situation is when the voltage stress is very even along the whole length and numbers of zinc oxide blocks. But this is only theory, but in reality we can only improve this area here on top, and we will provide a stress that is maximum 1.2 of our voltage. That means that we will maximum apply the typical voltage ratio on this block, which we have on the whole surge arrestor understood as continuous operating voltage. So this MOV block here on top can survive for the whole lifetime of the surge arrestor with the stress of maximum 1.2. Coming to an end, I want to make sure that you know that we are providing type test protocols for all those specific ratings we have talked about right now. We have a portfolio of products which are fully independent type tested at different test labs with big names. And we also have an internal test lab where we can conduct tests internally for development projects, but also for FAT or for special customer requirements. We can provide internal test protocols, and that's it. So here's the end. Thanks for your time.